ladies and gentlemen. This video is our introduction to what we refer to in chemistry as colligative properties. As a result of this video, you will be able to define the term colligative property in your own words and understand it enough that you'll be able to teach someone else how exactly a solute lowers the vapor pressure, raises the boiling point, and lowers the freezing point. And you'll be able to apply your understanding of the pure solvent phase diagram to predict how the presence of a solute changes. So how will a solution phase diagram compare? So let's dig in. First, we talked about solutions being mixtures. And we say that in a solution, being a mixture, the different components, your solute and solvent, because they're a mixture, they retain their own chemical identity. Even though they're combined, the solute is still the solute and the solvent is still the solvent. The water still behaves as water, and if the solute is sodium chloride, it's still recognized to be sodium chloride, or sugar, still recognized to be sugar. Well, there's a little altering of the properties of the solvent because of the presence of the solute. And we will focus on 3 colligative properties in honors chemistry. They are vapor pressure lowering, freezing point depression, and boiling point elevation. Now, we need to make sure that we understand we are talking about non-volatile solutes. Remember, the term volatile means it easily becomes a vapor. Well, you know that if we have sodium chloride dissolved in water, that the sodium chloride does not easily vaporize. In fact, the water, the solvent, vaporizes at a much higher rate than, of course, the sodium chloride does. It's non-volatile. In fact, if we let this sit long enough, the water will all vaporize and then we'll be left with undissolved solute. So we're talking about non-volatile solutes. So when it reads here that we're reducing the vapor pressure of the solvent in the solution, yeah, because we realize that the solute is staying put. We say that we lower the freezing point of the solution, but it's really the solvent. As far as we're concerned, we're just dealing with non-volatile solutes, and so we're talking about the change in the solvent properties, but we sometimes talk about, well, the solution's properties. One and the same for what we are going to address. All right, ladies and gentlemen, so what is unique about colligative properties? Well, colligative properties, strange for chemistry, do not depend on the identity of the solute. They depend on the amount. So it's the amount of the solute that is there. So the concentration of NaCl, what mass have you added? As long as it's soluble, we're not so concerned about, is it sodium chloride or is it potassium fluoride? You know, a colligative property, it depends on the amount that you're dissolving. As long as it's soluble, not too much on the identity. And we know how strange that is in chemistry because often the identity is what the associated properties go with. So, a colligative property depends on the amount of solute, not the identity. And again, going with that it definitely will be soluble. Okay, so what about vapor pressure? Well, I have a nice image here. So the flask on the left is just pure water, and we know water being a polar molecule, the orientation, it looks like a Mickey Mouse head, the red are the oxygen and the white are the hydrogen. And we know water being water in the liquid state, some of these particles will collide, get enough energy to overcome some of the particle attraction and vaporize. And we know the pressure that a vapor exerts on the liquid it vaporized from is vapor pressure. Because we also know that we probably have some nitrogen and some oxygen in there, just exerting air pressure. Well, what impact does the presence of a solute have? We observe that a solution has a lower vapor pressure than the pure solvent. But why? What we understand is this, that the presence of the solute reduces the available surface the solvent has to vaporize. So remember, we are talking about non-volatile solutes. So let's say this water molecule gets enough energy to become a vapor. Well, it's gonna, oh, look at all the barriers in the way. Now, of course, maybe if it scoots around that, it will escape. But there's barriers in the way where if it's just pure solvent, there aren't any barriers blocking it. Or it may collide into a water that then will escape. Where here, if it is colliding into a solute, there's just you have to put a lot of energy in to get the solute in the case of sodium chloride to vaporize. So it's because of the reduced surface area at the top. That is why. Now, of course, we know there's particle attraction between the solvent and the solute, but there's particle attraction between the solvent and the solvent. So it really is based upon the reduction of the area in which the solvent can escape. And you can understand that the greater the concentration, the less surface area that's available. So again, colligative property. It doesn't really matter what the solute is, just how many are there that is reducing the accessibility that the water has to be able to vaporize. So the presence of a solute lowers the vapor pressure of the solvent. And so in this image here, and I'll just get a little closer, this would be just vapor pressure versus temperature. So the black is the pure solvent. The red is a 1 molar solution and the blue is a 2 molar solution. You can see it's pretty much a direct relationship. So as we are increasing concentration, we are lowering vapor pressure. Again, a colligative property. It is absolutely based on just the reduced surface. Okay, let's go to boiling. Now, remember that boiling is defined as the temperature at which the vapor pressure equals atmospheric pressure. Okay, so we know at room temperature, if we say that we're at sea level, and let's go ahead and say that the pressure of the atmosphere is 1 atm. Well, vapor pressure of water is minuscule. So we have to input energy to get the vapor pressure of the water to equal the atmospheric pressure. Yeah? Well, what does the presence of a solute do? It lowers this even further. So usually, the pressure of the atmosphere is already greater than the vapor pressure of the water, of the solvent. And so we have to invest energy to get this to be equal. Well, now the presence of a solute lowers this even more. So we're going to have to invest even more energy to get the vapor pressure of the solvent to equal the pressure of the atmosphere to boil. So let me just kind of summarize why boiling point is raised. So the boiling point is defined as the temperature, right? When the temperature at which the vapor pressure of water, if water is our solvent, is equal to the pressure of the atmosphere. So the vapor pressure of water is equal to atmospheric pressure. And so the presence of a solute lowers the vapor pressure of the solvent. Therefore, more energy must be invested so that the vapor pressure of the water, which we could say is the vapor pressure of the solution, as long as it's a non-volatile solute, so that this is equal to the pressure of the atmosphere. Now, of course, we're not talking about, multiple degrees of change, but we could be talking about an increase of, 1 to possibly 10 degrees Celsius. So we know at sea level, water boils at 100 degrees Celsius. Okay, so this is when vapor pressure will equal atmospheric pressure. However, whenever we dissolve solute, the vapor pressure drops. And so we have to invest more energy, and it could be that depending upon the concentration, our water boils at maybe 100.9 degrees Celsius. Or maybe, again, depending upon the concentration, maybe 102.8 degrees Celsius. Okay, so boiling point raises when we add a solute. Okay, now freezing, it's a little beyond what we need to really be able to theoretically explain as far as honors chemistry. I think it's much easier for us to understand the relationship of vapor pressure and boiling. So, we need to know what the presence of a solute does to a solvent. And that, of course, the presence of a solute, it lowers the vapor pressure. And we can explain why. Because the presence of a solute reduces the amount of surface that the solvent has accessible to vaporize. And so we need to be able to understand the theory. The presence of a solute raises the boiling point. We can understand the theory because we know what has to be true at boiling point. So if the presence of a solute lowers vapor pressure, well then we're going to have to increase the input of energy to get vapor pressure equals atmospheric pressure to boil. However, with freezing point, all we have to know is the impact. And the impact of a solute is it lowers the freezing point. It's based upon the lowering of the vapor pressure of the liquid, but that's okay. We don't have to know the theory of that explanation. So, we know that we put salt solutions or salt on icy roads. And why is that? Well, it is the solute, when it is dissolved in the solvent, water, it lowers the freezing point. So we're hoping to keep it as a liquid, which of course the friction of car tires and the weight of the car going over the road sure does help keep water in the liquid state. And then when we add calcium chloride or sodium chloride and make a solution, that lowers the freezing point, which keeps it as a liquid, which makes it safer for driving. We also take advantage of freezing point depression in car radiators, using antifreeze to actually protect and increase the range in which we have the liquid state. Okay, so what does the impact of a solute have on solvent? Well, we know that if we're dealing with water, that it's going to have solid, liquid, gas. All right, and if this is 1 atmosphere, then we know that this is a phase diagram, and this would be pressure versus temperature, that this would be the normal melting and freezing point, and then this would be the normal boiling point. Well, what does the presence of a solute do? It raises the boiling point. It lowers the freezing point. So actually, the presence of a solute extends the conditions over which we have the liquid state, because we are increasing the temperature for boiling, and the more we add, the greater the change, and we are decreasing the freezing point. Okay, so if we take a look back at our objectives, I sure hope that you feel at this point you could accomplish. There are some questions at the end of the video just to help you measure your understanding. Best of luck.